Will be our third lecture on earthquakes, and I'm afraid it will be the longest one. We'll see how efficiently I can get through this. This will be earthquakes number 3, and in our textbook, this is chapter 9, earthquakes and faulting. And what we're going to do today is we're going to talk about measuring earthquakes for their energy, geography, and human suffering. All right, every aspect here is going to be about measuring quakes. This would be things like Richter scale, etc. But what it boils down to, measuring of quakes, in a lot of ways, is trying to get an estimate for that kinetic energy that's being released by the stored potential energy. It's this kinetic energy that causes the destruction. And the kinetic energy is released by some event. And it's the transformation of a potential energy. And the thing that takes the form of the potential energy probably is numerous, but the thing I want you to picture the most for the storage of the potential energy is going to be friction, and then this other word, which is a new one probably for you, which is asperity. And asperity is a type of roughness that locks faults together or plates together. And the simplest way you can think of that is, what if our plate boundary was like so, jagged, and one plate was moving this way, the other plate was moving that way? You can imagine how these irregularities lock the fault. Now, when it comes to big earthquakes at subduction zones, I want to show you what this might look like. It's at a seamount. So an underwater volcano that might get put into the subduction zone. Right, so imagine these seamounts like Hawaii, and here's the subduction going down underneath here with this is the axis of the trench. You can even see scars on the overriding plate for where these mountains are being thrust down under. And what if they're providing the lock, the irregularity, the asperity that locks the fault? Okay, so when that energy is released, it's released in the form of seismic waves. And we're going to go through 3 types of seismic waves today. And these are the majority of the energy that's released. The first type to discuss, and we've talked about these in some of the other classes, is the P wave. And the P wave is a compressional wave. And what compressional means is that the waves move material, the rock, parallel to the travel direction. We should say that. Move rock parallel, that's a symbol for parallel, to travel direction. And so if we were to have a P wave and our rock looked like this with these lines that were equally spaced, when a P wave was moving through it, some would be equally spaced, some would be closer together, and then we'd go far apart and then close together. And it's here and here where these P waves are really being able to be seen. P waves cause little damage. People say that maybe when you feel a P wave, it feels like you're getting hit by a truck or hit by a fence. There's a shock to it, but they don't cause much damage. They move fast and they arrive first. They go through liquids and solids. So if we were sitting at the Earth's surface and here's our house, the P waves would migrate up to us like so. Now, S waves, they are a little bit, we don't need a dash, it's just S wave. These are the second fastest kind of waves. And we're gonna let that S stands for secondary because they arrive second. But really probably the S stands for shear. But S can stand for both of those for this class. They move at about 60% of the speed of a P wave, so they arrive a little bit after, and with a predictable amount of time after. 60% speed of P wave. They move rock perpendicular. Let's say that. They move rock perpendicular, that's a symbol for perpendicular, to travel direction. And this is like flipping a rope or a whip in your hand. This is going to be the way that a particle would move as an S wave moves through it. If we're sitting in our house and an S wave arrives, this is kind of the thing you'd be able to visualize, which then could really start shaking. They do cause damage and destruction. The third type of wave is the slowest of all the waves, and we're going to call these surface waves. Surface waves can be categorized into other names, Rayleigh waves and Love waves. I want to just group them together. These are waves that only travel on Earth's surface. Notice in the previous two drawings of our house, the waves were coming from below. But that is not how a surface wave moves. If here's there's our house. Surface waves only move on the Earth's surface, and they can move like a snake back and forth, or they can move like a rolling ocean wave. These cause the most damage. So they are the slowest, but they also cause most destruction. Thankfully, they can't travel through the Earth, so they're more geographically restricted. All of these types of waves, both S, P, and surface waves, dissipate and become less powerful with distance. All right, we're making good progress through today's lecture. So now let's talk about measuring seismic waves, and we do that with a device called a seismograph. Seismograph. Sometimes you hear this named also as a seismometer. They are equal. And what a seismograph does is it will measure ground motion. With time. A lot of times there's like a pen. It's as simple as a device with a pen that is, imagine like a big like sheet of paper, and a pen gets dragged along that sheet of paper, and then the earthquake wave arrives, and then it goes away. That's all that really a seismograph does. Of course, they're more sophisticated than that. The look of a seismograph would be something like this, and it is a graph. So we have to talk about the axes, and on the y-axis it's going to be amplitude, and this is the amplitude of the shaking, and it's going to be measured in millimeters. And the x-axis is time, measured in seconds, and so the pen drags along the sheet of paper, and then the P wave hits, and then the S wave hits, and then the surface wave hits, and then the earthquake ends. And then maybe there's aftershocks afterwards. So let's label some of these features I just put in. The first arrival is the P wave. The second arrival is the S wave. The third arrival are the surface waves. And this would be like the hitting hard with the P wave, the rolling action, and then with the surface waves, the damage is starting to occur. And one thing I would like you to see between the P wave and S wave is there's some amount of time here, measured in seconds, which is critical for understanding where earthquakes occur and helping us mitigate disaster. And the first thing I'd like to talk about with that amount of time is it's called triangulation. And with triangulation, we're going to introduce a very simple formula. It is distance equals velocity times time. And distance, we want to figure out how far away from the seismometer was the epicenter of the quake. The V, this is our wave speed of P waves and S waves, and T is the amount of time in seconds between the P and the S wave interval. So let's say P minus S arrival interval. And by using the seismograph, we can get a number here of like 700 kilometers or 500 kilometers. And what that looks like would be a mathematical or a geographic thing set up that looks like this, where with one seismograph, all right, here's the arrival distance in one seismograph. What is that? That's station number 1. Using that amount of difference in time, we got a distance here of 2,000 kilometers. So from this seismograph, we know the earthquake had to have been 2,000 kilometers away from it, somewhere on that circle. Then we go to another seismograph, and at station 2, we know that it had to be somewhere along this circle. If you get a third, you can get more restricted, and at some point you actually get all these circles overlapping, telling us exactly where the epicenter of the earthquake is. You can do it with 3, but you could also do it with 1,000. All right, so that's a very important aspect of measuring an earthquake. Now the next thing is going to be the Richter scale. And as we get into Richter scale, I'm just going to say this. Richter scale plays well in the news. We've all heard of the Richter scale. It's an 8.0 on the Richter scale, but this is old. This is the old system. This system is no longer used anymore. It was a scale between 0 and 10, where 10 is a huge earthquake and 0 is a small earthquake, well, no earthquake, but that's not used anymore. Nowadays, we use a scale, very similar in name, and it's called the moment magnitude scale. And the moment magnitude scale also is a measure of the amplitude of the earthquake that ranges from 0 magnitude up to 10, and 10 would be a huge disaster. But it's just so much more quantifiable. And what the moment magnitude scale is what's reported in the news. It uses the wave amplitude, all right, how much shaking is on the seismometer. It also measures the amount of energy released, right, that was stored by the friction that was released in the form of waves, and importantly, the size of the rupture. So, like, how long of the San Andreas Fault actually ruptured? Was it 1 mile or was it 100 miles? Well, the 100 miles would have a much bigger moment magnitude number. Within this scale, there is a difference in ground motion between the numbers and energy released. So if we had a magnitude 4 versus a magnitude 5, the magnitude 5 has 10x ground motion, and it has 32x energy released. So the difference between just one magnitude is really important for the size of the earthquake. Imagine the difference between a magnitude 3 versus a magnitude 7. That would be 10 to the 4th ground motion. Right? What is that? That's 10,000 more motion. That would be so much more destruction. Okay, and then now to finish off, I want to introduce to you 3 other ways that earthquakes are measured. We'll just go like this. There are other ways. One of them is GPS, and we can see how much the ground moves after an earthquake on the order of centimeters to meters. And we can actually see the 2 sides of the fault move relative to one another because the GPS is so amazing. And then next figure, I want to show you something called the INSAR. And then finally, we're going to get to modified Mercalli. Put a picture in to introduce these 2 concepts, and then we'll be done for this lecture. So in these 2 pictures, we have a shake map on this side and an INSAR on this side. And what INSAR is space radar that measures movement. It's a lot like GPS. It's more beautiful in terms of its rainbow color. And we can see that in Haiti, there was this terrible, devastating quake that killed 100,000 people. Terrible. Worst in my lifetime. And we can see, based on how much the 2 sides moved in rainbow, we can see the displacement and the rupture length of the fault. The other picture here shows that in Haiti, there was an area of damage of red and then moving further away. And this is a scale of modified Mercalli, which is a map of, I guess you could say, destruction and human impact. Maybe it's a map of human suffering. And it's on the scale of 1 to 12 in Roman numerals, where 1, there's no damage at all, and 12 means total destruction. So in this, and if you want to see that, you can see it down here. Maybe this is too small font, but if you need to, search on Wikipedia. But in this area near Port-au-Prince in the island of Haiti, there were red colors. So the shaking was violent and extreme and heavy, and these houses in this developing nation were built to withstand hurricanes, not the shake of an earthquake, which is why it led to collapse. Now what's interesting to see is like Jamaica, these other islands, the rest of Hispaniola felt in the blues and the greens. And blues and greens mean they felt the earthquake, but there wasn't much destruction.